All right, everybody, we just got the go-ahead to get started. So welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today. And I'm up here in the pilot's booth behind you, waving my arms. Hello, everybody. Welcome. So today you're going to be watching Tour of the Universe, which is one of my favorite shows that we do right now because it is a completely live show. So a lot of the other shows that we have in here in the Morrison Planetarium are pre-recorded movies, kind of, with a short section where someone like me will talk to you. This show, however, is completely live, so I'm going to be flying around in our planetarium software and talking to you about the universe. And before we can do that, I do have just a few quick planetarium rules for us to go over. And also, sorry for the distraction on the dome there of the trivia keeping going. It did go away earlier today. It's not going away right now, though. Sorry about that. But anyway, just a few quick rules. First of all, please no eating or drinking while you're in the planetarium today. While you're following that first rule, the next rule should be easy to follow. Make sure to keep your mask on for the entire show. Even once the lights go down, make sure that mask stays on. If you have a cell phone, a camera, a tablet, anything at all like that that could give off light or sound, those can both be very distracting in here, so make sure those are put away during the whole show. And for your safety in this dark theater, and also to make sure that we're keeping up our social distancing guidelines here, make sure to stay in your seat until the end of the show. At the end, you'll hear my voice and I'll give some instructions for how we will exit the dome. And last but not least, if anything on the screen makes you feel any dizziness, any motion sensitivity, anything like that, go ahead and just close your eyes for a few seconds, and that will help your brain to remember that you're just sitting in a chair in a planetarium, not actually flying around in space, and you'll feel a bit better. And I'm going to give our lovely guest experience staff just a few more minutes here to seat the last few people. And then we will get started. And for folks that just joined us, just a few quick rules and reminders. Make sure there's no eating or drinking while you're in the planetarium today. Make sure to keep your mask on the entire show, even once the lights go down. Make sure to stay in your seat, and I'll give instructions for exiting at the end. And if anything makes you have any motion sensitivity, dizziness, anything like that, close your eyes for a few seconds, and that'll help you to feel a bit better. All right, so we are ready to get started with our tour of the universe. All right, so I'm having us start our tour today relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And I always like to start out these tours at the International Space Station because today we are going to be covering some amazing distances. We're going to go basically as far out into space as we possibly can today on our virtual tour. And something really cool about this particular presentation as well is that I'll be doing all of this with the OpenSpace software. So this is a free and open source planetarium software that you can download for free at home. If you want to do that when you get home, feel free to ask me about that after the show. And it's all database. So everything that we're going to be seeing today is based on actual pictures and data of the locations that we're going to be visiting. So right now, as we pull away from the International Space Station, and I'm going to bring up a line here to show you where the International Space Station orbits around our planet, you'll see below us the Earth going by as we go around the ISS. And the particular reason that I like to start at the ISS is that this is as far as humans travel out into space right now. There are always a few people on the International Space Station at any one time. You can fit about 6 or so astronauts inside of it. And we've had people living up there for about 20 years now, so quite a long time. But don't worry, it's not just 6 people that have been stuck up there for 20 years. They swap out every few months or so, or the most that any one particular person, the longest that one particular person has lived on the ISS was about a year. But today we're going to see generally how far our human influence has gone. So the ISS, pretty close by, is as far as humans travel out into space right now. We'll also see how far humans have traveled out into space in the past. But we're going to go way farther than that. We're going to see how far our spacecraft have gone, how far any of our signals have gone, and we're going to go even farther than that still. But you can see that yellow line of the International Space Station going around our planet. They're traveling very quickly. Only takes about 90 minutes to orbit us once. And we're seeing some data from this morning of where the different clouds and storms and such were around our planet. And kind of a fun thing I can point out here too is one of the ways we can tell this is real pictures and data. If you notice these kind of white areas, these white streaks, those are areas where they took the picture around noon and the sunlight was reflecting off of the surface of the Earth or the oceans. But I'm going to keep us zooming out. We're going to keep on moving here because I do want to take us out very, very far into space. But our next stop as we go away from our planet is our closest natural neighbor in space. And I say closest natural neighbor because we have a lot of human-made neighbors floating around out there as well. We have a lot of satellites that are going around our planet. But I'm going to take us to our, whoops, sorry, that was kind of fast. Remember to close your eyes if that makes you dizzy. We're going to go to our natural satellite, the moon. So the moon is as far as humans have traveled out into space so far. A little over 50 years ago, a few lucky people from the United States went to the moon. A dozen or so went there, half a dozen or so walked around on the surface. But this is as far as human beings have set foot away from the Earth out there in space, is our closest neighbor. But while it is our closest neighbor, it's still about 250,000 miles away from us. So nothing in space is close, really. And at the moon, I'm going to introduce an idea that we're going to be using for the rest of the show here. So we're going to be looking at distances that are almost impossible to comprehend. We're going to be looking at distances of millions or billions or trillions of miles and kilometers. So if I use distances like that throughout the show, if you're like me, that's not going to mean much to you if I start to use those. So I'm going to use a different measurement. I'm going to try using the speed of light. So if you can imagine the fastest speed we possibly know of anywhere in the universe and how long it would take for something traveling at that speed to go as a distance. So for example, you can see Earth in the background down there. If we were to travel from Earth to the moon, traveling at the speed of light, it would take us roughly 1.5 seconds or so. So about the same amount of time as it took us in our OpenSpace software to get over here. So not too long. So the moon is 1.5 light seconds away from our planet, if we're using that as a distance. And we're looking right now, since we can see Earth very clearly in the background there, we're actually looking at the side of the moon that you never ever get to see from here on Earth. The moon is orbiting and rotating just the right way that we always see the same side of the moon. So this is the far side of the moon that's always facing away from us. It looks pretty different from the side that we see. Far fewer Maria, those dark areas that we see on the near side of the moon. But I'm not going to stay here too long either, because again, we have a really, really, really long way to go today. So I'm going to keep us zooming out farther and farther. And I'm going to now bring up some more lines to show us some orbits of other objects in our solar system. So you're going to see a blue line for the orbit of the moon around the Earth. And as I zoom out, you'll also see some blue lines for the other planets in our solar system. And I'm next going to focus on the center of our solar system, the closest star to us, the sun. Now, if we were to use that light speed distance again, so again, if we were traveling at the speed of light, the fastest speed we know of, it would take us about 8.5 minutes to travel from Earth to the sun. So I also like to give people the idea of that. So when you go outside and you look at the sun, which first of all, don't do that, don't look at the sun. But if you were to look at the sun, that's what the sun looked like 8 minutes ago, not how it looks today or right now. Or the sunlight you see is 8 minutes old. So if the sun were to disappear right now, we wouldn't know about it for 8.5 minutes. But thankfully, there's no reason why that would happen, so we don't have to worry too much about that. But if we were traveling at the speed of light, that's how long it would take us to get there. And we're seeing the orbits of the closer, rocky, smaller planets here. You can see the orbit closest there of Mercury, then Venus, Earth, and Mars. We got this pretty sizable gap here, which is where the asteroid belt is. So that's where most of the asteroids are in our solar system. Mostly rocky objects in between Mars and Jupiter. And then we can see Jupiter, Saturn, and then we'll see the orbits of Uranus and Neptune. And we are going to be leaving our solar system behind entirely. But before we do, I always like to stop right around here and bring up our lovely, at least my favorite, dwarf planet, Pluto. Now, to this day, I still get people asking me why Pluto isn't a planet anymore. And sometimes people ask me, why do you hate Pluto? And I say, I don't hate Pluto. I love Pluto. But the reason that Pluto is no longer called an official planet, it's not part of those 8 planets that we talk about, has to do with where it orbits in our solar system. So you can see the asteroid belt in between Mars and Jupiter. There's also the Kuiper belt, which is much farther out by Pluto, with a lot of kind of icy objects and some rocky objects too. I'm going to turn on a whole lot of other lines here, so just a warning, it's going to look kind of bright. And a lot of these ones, these are what we call trans-Neptunian objects. These are objects that orbit outside of Neptune's orbit. If you watch where a lot of them are, you can see that they go along roughly where Pluto is in its orbit around the sun. So all these other objects out here, these small icy objects in the outer reaches of our solar system, they're the main reason why we call Pluto a dwarf planet and not an official planet. Just because one of our definitions for a planet is that it needs to clear its path. It has to be big enough to have shoved stuff out of its orbit, basically. And little Pluto was not able to do that, so it was changed to a dwarf planet back in 2006. But still a very interesting place. And just a few years ago, we sent the New Horizons spacecraft by it to get us some really nice high-resolution pictures. Which brings me to the next thing that I'm going to bring up here, a spacecraft that we have sent out into space. So we've seen so far how far humans travel right now, how far humans have traveled in the past, our moon, and now we're seeing how far our spacecraft have traveled. So we personally, people walking around, we have not set foot on things beyond the moon, but our spacecraft have gone pretty far. So these lines are showing us how far our farthest spacecraft have reached by now. So these are showing the trajectories of Pioneer 10 and 11, Voyager 1 and 2, and most recently, the New Horizons spacecraft, which went out to Pluto. But even with these spacecraft, which are some of our fastest that we've sent out so far, and they're the farthest, we're still kind of debating if they've left our solar system yet or not. Because there's a lot of things going around the sun. So it's kind of hard to determine exactly where the cutoff is of what's our solar system and what's officially beyond our solar system. But even with how fast they're going and how far they have gone, possibly to the edge of our solar system, none of these spacecraft have gone as far as light could travel in a day. So we're only out to light hours or light days of distance at this point. And we're already starting to leave our solar system behind. But while we might still be in our solar system at this point, it's a little tricky to decide. There is a certain point where I will definitely say we have left our solar system behind for sure. Because in a moment, you'll see the actual, true brightness of the sun. We were kind of dimming it down before so you could see things in our solar system better. So this is how bright the sun would look compared to the other stars out there in our galaxy. And as you can see, as we get far enough out, we're starting to fly past other stars. They're not looking like that flat blanket of stars like we see in the sky anymore. We're starting to see them as 3D objects that we're flying past. And the closest star to us, which if I'm looking correctly, it looks like it's just to the left of the sun there, Proxima Centauri, part of the Alpha Centauri system. That is a distance now, we're getting into light years of distance. So if we were traveling at the speed of light, it would take us about 4 years to travel from Earth to Alpha Centauri or Proxima Centauri. So the closest thing outside of our solar system, still, if you were traveling the fastest you possibly could, would take you several years to get there. But we're not stopping there because we still have a long ways to go. We're still zooming out away from the sun, starting to kind of blend in with some of the other stars in our galaxy. And I do have one more place for us to check in on our human influence out here in space too. So we've seen how far we've gone. We've seen how far our spacecraft have gone. But there is one more thing that we're sending out into space, and we can track how far it's gone as well. And that is any of our radio signals or TV signals, any signals that are strong enough to leave our planet, we can see how far they would have gone, which is called the radiosphere. So I'm going to bring that up now, our little model of the radiosphere. So this blue sphere is to show how far any of those signals could have gone by now. So we've been sending out radio signals and such that were strong enough to escape our planet since about the 1920s, 30s or so. So this is roughly 80 or 90 light years away from the Earth in all directions. So that's the edge of our human influence out here. That's as far as anything we've sent out could have gone. So that may make you wonder, well, if this is how far anything we've sent out has gone, how do we even know about the stuff beyond that? And that's where we get to the main way we know much of anything out here in space is just looking for stuff with our telescopes. So the majority of the stuff that we see out here, we learned about it because the light of these stars, the light of these objects came to Earth and they got into our telescopes and we were able to study them that way by looking at the light that they give off. And sometimes we look for the effect on these stars as well, especially if we're looking for these objects. So every single one of these blue circles I've put up here are showing us where we've found planets, exoplanets, planets outside of our solar system. So we find these in a number of ways, but sometimes we look at the star and see if there's any sort of dip in the brightness of the star as a planet passes in front of it. That's how we found a lot of these exoplanets. And we're finding so many of these. These are just the ones that we've seen so far, we've mapped, and we know for sure that they are exoplanets. And we have found over 4,000, but there's thousands more that are candidates for being exoplanets. So planets, things we think are exoplanets, and we just have to watch them a bit longer to see if we're correct. But these are the ones we found so far. But we're going to keep on going. And I'm going to bring down our exoplanets, but I'm going to keep on the radiosphere. I always like to keep that on as we zoom out, see how long you can spot it as we go farther and farther. And we're starting to transition our model here. So before we were looking at a model of individual stars that we've seen from here on Earth, that we've mapped out where they are relative to us. But now we're going to kind of switch over to a model. So by a model, I just mean this is not a picture. This is not an image of this object. So we're looking now at a model of our Milky Way Galaxy. So what we think our Milky Way Galaxy would look like if we could go outside of it. Because as you saw, we have not sent any spacecraft out this far. So we have a pretty good idea of what we think our galaxy looks like, but it's based on what we see outside our galaxy and what we are able to see from where we are in the galaxy, since we can't go out there and just snap a picture. But our Milky Way Galaxy, it's made up of billions and billions of stars, just a few of which we flew past and saw as we were closer to the Earth. And out here at this distance of looking at our Milky Way galaxy, we're now up to thousands of light years of distance. If we were to travel from one side of the Milky Way to the other, it would take us about 100,000 years if we were traveling at the speed of light. And you can still just barely see that little blue dot there. See if you can point it out, this little blue dot right there. That is the radiosphere. That's how far all of our radio signals have gone so far. But I'm going to keep going. We still have quite a ways to go, actually, because as we pull away from the Milky Way galaxy, we're going to start to see a lot of other dots showing up. And these colorful dots that we'll see all over the place, these are no longer individual stars. Instead, these are showing us individual galaxies. So every single one of these dots that we're seeing, these are each their own galaxy with their own billions or sometimes trillions of stars. And I like to point out the colors of them as well. Lots of different colors we're seeing here. These are not the colors of these galaxies, though I do think it would be fun if there were just cosmic skittles all over the place out there in the universe. The colors are based on which data set those are part of, which telescope found them, where they are, how they're grouped together at different parts of the universe, things like that. So we like to use different kinds of color coding to sort things that we see out there and when we map them out in the universe. And this is a map. This is an actual map of where we have seen these galaxies, and we've plotted out where they are relative to us. But since this is an actual map, if I get far enough out in just a minute, we're going to see that there's kind of a strange shape that the galaxies seem to form. It's going to look, well, we're almost there. We'll see it in just a second here. It's going to look sort of like an hourglass or a butterfly. Looks like I have a weird angle. Let's see. An hourglass or a butterfly. Or sometimes people think it looks like pasta. But the universe is not shaped like a butterfly, unfortunately. I think that would be fun if it was. But this shape that we're seeing now is because we're mapping this, and this is what we see from our perspective here on Earth. So the gaps that you see now on our kind of bottom right, top left there, those are because we just haven't been able to map out everything yet. So we live in a galaxy too, the Milky Way Galaxy, and our galaxy has a lot of gas and dust and stars, and a lot of stuff that's in our way when we try to look out into the universe. So when we look over in those directions, our galaxy is blocking our view, making it harder to see the galaxies that we're almost 100% certain would be there. So we just haven't mapped out everything yet, but there should be just as many galaxies over in those directions as in the other ones. And at this point, I also like to point out that we've gone, I think I would guess, a few billion light years now away from the Earth. So if we were traveling at the speed of light, we would have been traveling for a few billion years by this point. And at this point, we're also really looking far back in time in a way. If you remember at the beginning of the show, I mentioned how if you were to look at the sun, which by the way, again, don't look at the sun, but if you were to look at the sun, that's how it looked 8 minutes ago. Well, this is what our universe looked like billions of years ago. Because this light, it takes so long to travel to us and get into our telescopes that by the time it gets here, we're seeing the light as it looked in the past. So because of that, there's only so far that we can go. There is an edge to everything we can see in our universe. And that limit we're about to see all over the place in just a second here is called the cosmic microwave background. Now, when you walk outside and it's a nice clear night and you can see lots of stars up in the sky, you don't see this everywhere you look in the sky. Thank goodness. That would scare me if I looked up at the sky and saw this everywhere. But if you could see microwave light, a less energetic form of light that our eyes can't see, but a lot of our telescopes can, then you would see this every single place you look in the sky. And this is the earliest light that we can see and map out, and we know where it is. This is a few 100,000 years after when the Big Bang would have happened, when light was first able to expand out in all directions. So before this, everything was in a very tight, small area. Any light that was around, any light particles kept bumping into all the other particles that were there at the time, couldn't really go anywhere. But this is the moment that things cooled down and expanded enough that light was able to escape and expand out in all directions. So you can kind of think of this as the baby picture of our universe, the earliest light that we can see. But since this is the earliest light that we can see, and as far as we could possibly go out into the universe, that means I can't take us any farther. So we're going to end our tour today by flying on back home. Now, if we were really traveling at the speed of light, this journey would take roughly 13.5 billion years. But thankfully, we're in the planetarium, so it should only take us about a minute or so. So here we go. And as we fly on back home, I want to leave us with one final thought. All of this that we've been looking at, all of these stars, galaxies, planets, dwarf planets, cosmic microwave background, all this stuff that we can see is a pretty small part of all the stuff we know to be out there in the universe. We know of a couple of mysterious things out there in the universe, dark energy and dark matter. And we call them dark energy and dark matter because we're not quite sure what they are. Dark energy is some mysterious thing that is causing our universe to accelerate as it expands. Dark matter is some mysterious substance that doesn't seem to interact with light, but we see effects of it all over the universe. And we know that those two things, dark energy and dark matter, if you combine them, they make up about 97% of our universe. So all this that we can see and map out, that is just a tiny portion of what we know is out there. Now that often, understandably, makes people feel kind of small, that we're this one little tiny dot in this gigantic universe. But while I get that, and it does also make me feel kind of small sometimes too, I also think it's pretty exciting. Because look at all of this that we have found, we have seen, we've mapped out, we know where it is, we've seen it with our telescopes. And there's a whole lot more out there for us to discover and learn about. And that's pretty exciting. So with that thought, we're going to re-enter our, I think, more comfortable home realm of our human influence out here in space. We're going to go back into the radiosphere here. I'm going to turn it off so it doesn't get in our way. And we're going to head back to that closest star to us, the sun, which we'll see approaching us in just a minute as we get back into just a few light years away from the sun. And finally, as we re-enter our solar system here, we're going to head back to the third planet from the sun, where we've sent all these spacecraft out from, where we're able to look out with our telescopes and learn about these amazing places. And the only place so far in all of this that we have found life at all so far, which is pretty incredible to think about too. And we're back home. Hooray! So with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying through space with me today, and I hope you all enjoy the rest of your day. Thank you so much for coming.